students, welcome to online GDC classes. So in this today's pharmaceutical analysis session, we are going to discuss about ion exchange chromatography. So in chromatography technique, there are so many types of separation techniques are available. In this today's session, we are going to discuss about the ion exchange, how it is going to take place and how this is going to useful to us in pharmaceutical applications or any other applications, how this ion exchange is going to take place. Okay, let us go inside of these slides. First of all, let us see the definition of this ion exchange chromatography. Ion exchange chromatography is a process by which a mixture of similar charged ions can be separated by using an ion exchange resin, which exchanges the ions according to their relative affinities. Okay, exchange resins will be there, which are going to act as the stationary phase, and according to the oppositely, that means similarly charged ions, how they are going to be separated by exchanging the ions. Okay, which are actually based on the according to relative affinities of those ions, it is going to take place. Ion exchange chromatography is a type of adsorption chromatography, and this is a reversible exchange of similar charged ions is going to take place. Mostly similarly charged ions like cations and anions can be conveniently separated by this technique. Many drugs and pharmaceutical agents are weakly or strongly acidic or basic in nature, right? Most of the compounds are either weakly acidic or weakly basic in nature, and some of the compounds are going to be very strongly basic. Hence, a mixture of similar charged substances can also be separated into the pure components. So this chromatography is going to helpful to us in order to separate the similarly charged particles, similarly charged substances. Coming to the principle of separation involved in this ion exchange chromatography, this is by reversible exchange. That means similar type of the ions are going to be separated according to the oppositely charged attractions. That means reversible exchange of the ions between the ions present in the solution and those present in the ion exchange resin. That means in the resin it contains positive particles, automatically it attracts the negative particles. Then it exchanges with that. So that's why it is a reversible exchange. Okay. So cation exchange, anion exchange. There are only two types. Cation exchange means what? The separation of the cations using the cation exchange resin. It is going to be actually called as cation exchange resin. Actually it contains the negatively charged particles. Okay. The cations to be separated are present in the solution and exchanges for similar ions present in the cation exchange resin. That is a solid matrix, which is going to be called as. And the exchange can be represented by this following equation. That means X, which are going to be actually the sample contains the positively charged ions, and R minus K plus. So that means the resin which is going to be there, then it is going to exchange like this, X plus and R minus. Okay, and positive ions are going to be separated. So here you are going to observe the exchange is going to take place, which are the samples are going to be given in the form of solution. So this is also in the solution, this is also in the form of solution. That means two liquids. Okay, and the cations, whatever those are retained by this solid matrix of this ion exchange resin, can be eluted by using the buffers of the different strengths. That means the mobile phase, the buffers of the different strengths we are going to use, and separation of the cations can be affected. Okay, based on the retention of the solid matrix only, this ion exchange resin is going to play a very key important role. So we are going to use some different types of the buffers as mobile phase. So the strength of the mobile phase is also very important, so that sometimes the strength is going to affect the cations also. And coming to the anion exchange, separation of the anion using anion exchange resin can be carried out, and the anions to be separated are present in the solution and exchange for similar ions present in the anion exchange resin, that is a solid matrix will be there. Okay, so it can be represented by this following equation, that is, if the solution contains these negatively charged particles and the resin contains R plus and Cl minus, then how this exchange is going to take place? X minus R plus, it is going to form a complex here. That means exchange is going to take place, thereby chloride ions are going to be eluted out. Okay, so this has to be actually in the solid state, and this solution is going to be taking place. Here we are going to take the solution, thereby the solid matrix, it is the separation is going to take place. Okay, and the anions which are retained by the solid matrix of this ion exchange resin can be eluted by using the buffers of different strength, and has separation of the anions can be affected. Okay, similarly like cation exchange, anion exchange, but here the exchange of the ions are going to takes place by using the buffers of the different strengths, but in solution state in case of the cations, whereas in case of the anions, solution state it is going to be taken care, and afterwards the separation anion exchange is going to take place on the solid matrix. Okay, so that is what the difference you are going to observe here. So these are the pictorial view of how the resins are going to be prepared. That means if you are going to observe the anion exchanger, that is stationary phase particle, if it is an anion exchanger which is going to be called as, that means it contains inside the positive ions, covalently bonded positive ions will be there, and automatically it attracts the negatively charged particles. Okay, that means negatively charged anions are going to be attracted towards this. That's why it is a anion exchanger. But inside that you are going to observe the positive ions, but it is going to exchange the anions present in your sample solution. That's why it is an anion exchanger. Similarly, cation exchanger means it is going to attract the positive ions, that is cations are going to be attracted because it contains, the resin contains the negatively charged particles. Okay, so that's why ion exchange resin should have the following requirements. What are those? It must be chemically stable and should be insoluble in the common solvents, and should have a sufficient degree of the cross-linking should be there, and the swollen resin must be denser than the water, and it must contain sufficient number of the ion exchange groups. Whatever the resinous material we are going to use as stationary phase, it should contain sufficient number of the ion exchange resins. That means whatever the sample we are going to add, all those ions, cations or anions, whatever those are present there in our sample solution, it should exchange with the anion exchange resinous material. Okay, so the sample loading is also very, very important, and the number of functional groups present in these resins are also very, very important. So all these properties the ion exchange resin should have, whether it is an anion or cation exchanger. Okay, so this is a pictorial picture which is related to the exchange of the how this ion exchange chromatography is going to be working on this. If you are going to add the sample, okay, sample loading means which contains both positive and negative ions, then how these resins are going to be taking exchange of this. That means immobilized anion surface that is negatively charged here, and this is going to attract the positive ions. Okay, so afterwards how you can see, so positive ions, how these are going to be that means here you are going to contain the negative and positive. Okay, so how this orange color, focus on this orange color, how these are going to be not binded to these resins. Afterwards they are going to increase the buffer ratio. So here if you observe the positively charged protein with immobilized anion surface, it is going to be like this. It is going to elude these other particles. Thereby if you are going to observe here the negative ions and positive ions, okay, that means example sodium chloride if it is there, okay, sodium ions and chloride ions, how these are going to be separated out. Okay, and all these eluted with the low salt gradient and eluted with the high salt gradient. Different strengths of the buffers we are going to use. Based on the strength of the buffer, the elution order is going to take place. Okay, first of all sodium sometimes, then chloride ions are going to be eluted out. Okay, then we are going to see the detector response like this, time versus detector response. You are going to able to separate all the ions according to the retention time. Okay, coming to the classification of this ion exchange resins, how we can classify based on the source of the resin. First of all, based on the source of the resins, how we can classify natural and synthetic. So natural resins, nothing but zeolites, clay and dolomite. Synthetic resins like organic resins like polystyrene and divinyl benzene. These are the materials which are going to be used as the resin materials. And chemical nature, that means based on the functional group which is present in that, they have divided into 4 types: strong cation exchange, weak cation exchange, strong anion exchange, weak anion exchange. These are the examples of the functional groups which are going to be used as the resinous materials. That means sulfoxy groups, okay, carboxylic groups, amino groups, all these are going to act as strong and weak anion exchanges. Okay, if you are going to talk about this amino groups, primary amine, secondary amine, tertiary amines. Okay, so secondary amines, that means NH2 if you are going to talk about, and these tertiary amines which are going to talk about, these are the weak anion exchange resins. These are going to act as weak anion exchange resins. So based on the functional group, they are going to categorize this. And structural type of this resins, exchange resins, means like pellicular type with ion exchange film, porous resin coated with exchange beads, and macro-reticular resin bead, as well as surface sulfonated and bonded electrostatically with anion exchanger. Okay, so these are the 4 types of the resins which are going to be classified according to the structure. So pellicular beads will be, exchange films will be there, and porous resin coated. So if you see the pictures related to this, so this is a picture related to pellicular type films will be there, and here porous resins like this will be, you are going to observe here. And if you see this micro reticular beads, okay, so this is a micro reticular like a leaf, in the leaf how we are going to observe the reticular beads and like this. So this is about the macro reticular beads will be there. And finally surface sulfonated and bonded electrostatically with anion exchange. This is sulfonated beads. Okay, so these are the how the structurally related resinous materials they are going to prepare. Now let us move to the practical requirements for this ion exchange chromatography. That means whatever the column or which we are going to use as resin, exchange resin, that column material and dimension, this is also very important. And type of ion exchange resin and the selection depend on the following properties. What are those? Type of the ions, anions or cations, nature of the ions, that means acidic or basic, efficiency of the resin, how it can separate, okay, particle size of the resinous materials are also very important, and structural type like what we have discussed. Okay, structural type of the resinous materials, like means in the previous slide we have seen these are pellicular type resins or porous type resins, macro reticular type, surface bonded. So that is also very important, and column type of this exchange resin is going to play very important role in such case. And packing of the column, how we are going to packing ion exchange. Mobile phase, what type of the mobile phases we are going to use, like acids or alkalis or buffers, which type of the mobile phase solvents we can use it further. And development of the chromatograph, analysis of the elute, as well as regeneration of the ion exchange resin, because ion exchange is going to take place continuously between the oppositely charged ions. So there may be a lot of disturbances in the bed also. So regeneration of the resins is also plays a very important role. You might have seen in your household purposes how these RO water systems are going to be used, and frequently how they are going to maintain this, because in our water purification system also the main principle involved in this going to takes place, that is reverse osmosis. The ion exchange is going to takes place. All the ions are going to be removed by these exchange resinous materials only. Okay, so thereby the column beds are also going to be disturbed in throughout the passage of all those ions. So regeneration of the resins is also very important. Then ion exchange capacity, how we can calculate this ion exchange capacity. It is a total ion exchange capacity in terms of the exchangeable functional groups expressed in the milli-equivalents per gram of the ion exchange resin. Okay, so this is a formula for this. It is going to milli-equivalents per gram, it is equal to 1000 per equivalent weight. That means the particle size of the resin, porous or pellicular, whatever we are going to use, the particle size is very important. It is going to affect your ion exchange capacity. Amount of the cross-linking agent, which is also decides the swelling of the resin. The resinous materials are going to be cross-link, polymers are going to be used. So due to the passage of the solution, the swelling of the resin is also going to takes place. Thereby the capacity of the ion exchange is also going to be varied. Okay, so packing of the column, wet packing method is generally used, and mobile phase, which are going to be used as organic solvents, are less useful, but they are not used at all. Like acids and alkalis and buffers are used as eluting solvents only. Okay, organic solvents means easily they get evaporated, so we are not going to use only acidic solutions or basic solutions, and all the buffer solutions only we are going to use it in the ion exchange chromatography. Like examples like 0.1 normal HCl, 1 normal NaOH, phosphate buffers, acetate buffers, borate buffers, okay, phthalate buffers. All these buffers are mostly different at different strengths. We are going to use it in the ion exchange chromatography. So ion exchange capacity can be calculated by using this formula. That means based on the functional groups, it is going to change the milli equivalents per gram. So if you see the milli equivalents per gram is equivalent to 1000 by equivalent weight of the particular resin. Okay. So this is how this ion exchange chromatography, the setup, if you see, it is like a column only. So this more highly charged molecules are more tightly bound to the resin and so travel slowly and elute later. Okay, these are the more highly charged molecules, more tightly bound to the resin, so travel slowly. So we are going to pour the mobile phase from top, but these material, whatever those are in this pink color, which are going to be here, they have represented like this. Okay, how these are going to be bound to the resin. So if this is an anion exchange resin or cation exchange resin, whatever it is, so how these are going to be bound like this. Okay, so this pink color, it represents here how these are going to bind like this, and blue color, if you see, if you are going to observe like this, moderately charged molecules equilibrating between the resin and moving buffer more readily, moderately polar or moderately they are going to binding between the stationary phase. Okay, and if you are going to see the red color, they are going to be not having high binding towards that. That means less charged molecules bind less strongly to the resin and equilibrate with the moving buffer more readily and so travel rapidly and are eluted very soon. Okay, so that means the binding is not that much. That's why, so while adding the mobile phase itself, it move fast, thereby elution is going to be fast. Okay, like this they are going, we can understand the binding capacity, how this ion exchange is going to take place. And coming to the analytes of the elute, how these analytes are going to be detected, fractions are going to be collected in the ion exchange, and how we can detect those fractions. Several methods of the analysis can be used, which depends on the nature and quantity of the sample. That means if you are going to collect one fraction, then you can purify that and you can identify by different reagents or different methods of the analysis. Like what are those? If you see spectrophotometric method, that means either UV are visible. By placing in the UV cabinet also you can identify which compound might be. Polarographic method, if it contains some ions, okay, so electrolytic substances are there, then you can go for the polarographic method. Conductometric method, because almost anions and cations, that means compulsory you are going to observe some anions and cations there, they are going to have the conductivity property. Okay, so thereby you can go for this conductometric detection also. Amperometric detector, so ions there means they may also generate some of the current, thereby amperometry is also going to be one of the technique. Flame photometric method, some of the elements are going to be present, so if you are going to take that fraction and purify it and put it in the flame photometry, you can observe some of the colors, thereby this is also one of the technique. And radiochemical methods like Geiger-Müller counter and ionization chamber method. Okay, some of the radio elements are also going to be separated by using this ion exchange chromatography. Then you are going to use these methods, Geiger-Müller and ionization chamber methods. These are specifically used for the radiochemical compounds. Okay, so after analyzing, similar fractions are mixed in order to get pure ions or compound of the each. That means we are able to identify which type of the compounds are the similar. So by collecting the fractions, which fraction is similar to which one, then you can combine those two. Otherwise you can separately also you can use those compounds. Okay, coming to the instrumentation of this ion exchange chromatography, so it looks like normal liquid chromatography only, but the stationary phase, how we are going to column chromatography in HPLC, how we are going to use the different components. Okay, like this here we have given a schematic diagram. If you see this eluent, which is going to be, that is nothing but a mobile phase, this is going to be pumped through the system by a pumping system. Okay, pneumatic pumps, reciprocating pumps, like that systems are also, pumping systems will be available, and from the pump the mobile phase is going to travel into the column. Okay, so this is either anion exchange column or cation exchange column. Based on the properties of the compounds we are going to use it. So here they are going to use a 10-port switching valve. If the compound is anion related, then go for the anion exchange column. If the compound is cation exchange, that means cations are present, you can go for the cation exchange column. Okay, like that you can switch that, column switching will be there. And afterwards you are going to inject the sample while afterwards simultaneously. Okay, so this is the injection valve, and whatever the extra sample it is there, it is going to go into the vent or drain system. After the column, then the separation is going to take place on the column. Afterwards it reaches the detector. So either conductivity detector, UV detector, photometric, flame photometric, whatever the detector we are going to use. So it reaches the detector. Thereby you are going to analyze the data by using a suitable software or integration system. Okay. So similar, which is the instrumentation is quite similar to the HPLC only, but only the difference here is the column. Okay. And the factors affecting this ion exchange separations, let's have a look into that. Nature and properties of the ion exchange resins, that means cross-linking polymers are used here. So cross-linking and swelling is important factor which depends on the proportion of cross-linking agent, and that is polystyrene. Okay, so when more cross-linking agents are present, that is more rigid but swells very less. So when swelling is less, separation of the different sizes is difficult as they cannot pass through the pores present and become selective to the ions of the different sizes. Okay, that's why the properties and nature of the exchange resins is also very important. So more rigid columns are also you cannot use because the swelling is going to be very less. Then the different sizes are not going to be trapped. Okay, the beads or whatever it is going to be present in the column. So it has to be trapped there. Coming to the nature of the exchange ions, that means exchanging, because anions are present in your sample means you are going to use the anion exchange resin. So the nature of the exchanging ions is also very important. Okay, if your sample contains some chlorides and bromides ions, okay, how this anion exchange resin is going to act on this. So valency of the ions is also very important, size of the ions, as well as polarizability and concentration of the solution. High loading, not more than 2 mg per ml, you need to use it. Okay, similarly concentration on the charge of the ions. Okay, completely anions and completely cations if you are going to use it. That means the concentration is also very important, because sometimes they are going to build up some conductivity. Okay, so thereby one suppressor is also required in order to minimize that conductivity value. Okay, now let us have a glimpse on final slide, that is applications of this ion exchange chromatography. That means where it is going to be helpful. Conversion from one salt to the other, that means example, you can prepare tetrapropyl ammonium hydroxide from a tetrapropyl salt of some other anion. This is one of the application. Tetrapropyl ammonium hydroxide, we can prepare this by using a tetrapropyl salt of some other anion. Okay, thereby the exchange is going to take place. So ultimately we will get this compound. Okay, so in that application you can use this ion exchange chromatography. And household purposes, mainly the water filters, whatever we are going to use to get the soft water. From hard water, how we are going to use the collection of this soft water, we can use this ion exchange chromatography. And this ion exchange is used to prepare the deionized water, that means to remove all the ions, as well as separate and purify the metals. Some of the metals are also can be separated. And dealkalization, desalting, dealkalization is also can be done. Analysis and purification of the immunoglobulins. Okay, IgG, immunoglobulins, IGF, all these immunoglobulins also can be purified by using this, because high molecular weight compounds we can go for it. And separation of the inorganic ions also we can do. And assay of the 𝘾𝙀𝙎𝑏 and 𝘾𝙀𝑒. Okay, so these are actually the pharmacopoeially official in USP/NF, they have mentioned about these applications. Ion exchange chromatography can be used as official methods in the assay of 𝘾𝙀𝙎𝑏 and 𝘾𝙀𝑒 in drug substance as well as drug product monographs. That means in the formulation products also you can use this ion exchange chromatography for assay of these two compounds. Okay, officially they have done. And USP/NF chapter number 345, which contains assay for the citric acid or citrate and phosphate. So this assay is also going to be officially they are using this ion exchange chromatography technique. Okay, and another compounds like risodronate sodium assay, for this compound also we can use this ion exchange chromatography, and these are officially available in the pharmacopoeia. And if you are going to use some limit test, limit of N-methyl pyrrolidine, this limit test we can go for the cefepime hydrochloride compound. So in this compound, to determine the limit of this N-methylpyrrolidine, you can use the ion exchange chromatography. And assay and limit of acetylcholine test. For this acetylcholine test also, in methacholine chloride compound, you can go for the ion exchange chromatography. And organic impurities and limit of ammonia test. In the sample of heparin sodium, organic impurities test has to be done. Then you can go for this ion exchange chromatography. And ammonia test, the limit of ammonia, whether it is present or not in sodium bicarbonate, you can go for the ion exchange chromatography. Okay, so all these last 6 applications, actually these are listed out in the pharmacopoeias itself. So that means ion exchange chromatography is highly useful in determination of all these compounds. Okay, so these are the few applications of this ion exchange chromatography, and these are the concepts which are related to ion exchange chromatography. Okay, so thank you students for listening. Hope you understood well. Thank you very much.